Right. So as I mentioned, it's going to be all about all these webinars is generally going to be about image analysis, but we discussed and thought would be a good idea to at least start off. What I'm going to do is turn off this video, so I don't have to subject you to my face the entire time. Well, what we wanted to do was at least give you a quick crash course on the basics of image optics and formation. And this is so that you could at least see how the importance of getting it right the first time when you're under the microscope, because let's be honest, it's garbage in and garbage out. There's no amount of image analysis, deep learning, machine learning that could pull data out of an image that you haven't taken properly or is compromised or corrupted in some way. So this is just a quick little thing that we put together, hopefully let you get you familiarized with the concepts of getting from A to B on a microscope and getting the most out of your time on the microscope. So are we going to move forward here, or we're going to have to take this up? Okay, good. So some housekeeping and subsequent meetings. So the webinar series is going to be hosted obviously on Zoom, and even if we come back, if and when that happens, we're probably just going to keep it on Zoom because there's no guarantee that the meeting rooms will be open by then. So we're just going to have this all hosted on Zoom. The dates are tentative, and we will update you with the same Google Forms and send everything out so you can keep track of it. But you can see we're going to kind of escalate a little bit in terms of how basic the image analysis will be. And then we're going to get all the way to kind of the next gen ways for you to look at your data. Some housekeeping. So during this time, for the users of the HBIAMP, we've set up some remote desktop connections to some of the most used software at least. And this has been working pretty well. I just want to remind people to book online on the FACES system, because this is still a booking, whether it be remote or not, and try and put the application name and the fact that it's remote in the description so that it helps us kind of figure out what's going on. We've had some issues where people are kind of logging in without booking and unfortunately kicking people off or on the session. So we want to ask you to quit doing that. And if you keep doing it, we will take away your access and block your IP addresses. So there really is no reason to do this. So just try and follow the rules, and everyone will be happy. We had some complaints that these desktop connections are really slow for file transfer. Unfortunately, this is inherent to the protocol because it has to use all the bandwidth to keep up a nice little connection there for you to see the screen. We're going to work on a solution for now and get back to you as soon as we can. Hopefully we won't have to do this for too much longer, but just bear with us for a second. Some of you already have critical designation and are working in the lab already. Vincent is there right now, but the staff of the AMP will be kind of cycling through very sporadically, so we're not always going to be there. So if you do need help and none of us are there, I've set up Windows Remote Assistance on a lot of the machines. If it's not there, then it's not set up. But basically, you double click on the desktop icon and then kind of follow the prompts. Email us the invitation and the passwords, and hopefully we'll be able to help you remotely. So when we get back, and the people who are already back, things will be a bit different, obviously, just like everything else in our labs. So for the people who are in the main lab, just kind of, you know, it's a small lab, and we've crammed a lot of instruments into this. So just make sure that you look at adjacent systems next to you when you are booking, so you know that you're not going to be standing next to someone, you know, for an hour, 2 hours, or 3 hours. Same goes for the cell culture room. There's a little bit more space in there, but just keep that in mind. Try and book on different times and days just to try and avoid people. The people who are more experienced can go ahead and book, obviously, on the weekends and the evenings when there's less people around. This is just a reminder to, you know, no booking in the middle of the day. If you're going to book, book either in the morning, in the afternoon, like past noon, or the full day. So no 11 to 3 and messing everybody up. And try and leave about 10-15 minutes between each booking, or at least for the next person. This gives everything time to settle down, and of course it also gives yourself some time to clean the stations now, which I'll go into, because now we're going to have to make sure that everything's cleaned up nicely. If you're sharing the lab, we need you to wear a mask, and it's just good protocol. So just make sure you wear a mask if you're in there with some other people. If you're working alone, especially if it's at night or anything, just make sure that you let people know where you are. Please keep all the internal curtains and doors open, just to maintain circulation. The confocals are really good. The pinholes are always closed, so the light is not going to affect you very much. So don't pull those curtains closed, please. Very quickly, this is now the protocol before using each system and after the system. Wash your hands before and after, obviously. We need you to wear clean gloves the whole time as you're operating it. So clean gloves, just to keep them on, and this will kind of protect you. If you're going to be using eyepieces on any of the scopes, we ask that we're going to provide some cling wrap to kind of wrap over the cups, because we all know that the transmission is pretty prevalent if you put it through the eyes, and the eye cups of the eyepieces are going to be pretty bad. So we're going to cover them with cling wrap, and then we're going to have some disinfected safety goggles if you don't have them to wear, if you don't have glasses or whatnot. So and then after, you want to remove that plastic and disinfect everything. Obviously, you don't want to spray the equipment directly. No spraying of the expensive equipment, common sense. Just the stuff that you've touched. And again, wash your hands, and usual common sense applies. And we've got signs reminding you of this throughout the entire lab. So, but if you have any questions, let us know. We want to make sure that we keep up the status quo, so that we don't have an incident and then everything has to shut down again. I'm sure you guys are sick of that. So try and follow the rules if you can, please. So talk outline. So this is going to be a crash course. It is not exhaustive. It's just kind of something to think about for those who use a microscope, probably have forgotten from the training that they've done years ago, or just want a little bit of a refresher on kind of the basic concepts and the little things that you should be thinking about when you're sitting on the microscope, so you don't have to go back and re-image because your images and your data turned out to be crap. So, which unfortunately happens more often than not, if you believe. So I'm going to be talking about basically how the light gets from A to B. So refraction and optics, how to choose a lens, then all about resolution and how you sample your data. Digital sampling and dynamic range, concepts that people unfortunately don't quite understand and tend to ignore. And then we'll finish off with alignment and repeatability. This is just for you to see how complex a system can be, and things that can go wrong, and how you can keep track of what you can and cannot control. Right, let's just start off with refraction and optics. So the major components in microscopes are basically glass, and what that glass does is kind of herd the light in the direction that you want. And it's simply put, basically the concept of refraction, which is the change in the direction of the wave propagation due to the change in the transmission medium and speed. So you see the very nice examples here of just the light going from air to glass to back out to air again, and then this is just air and water. Everyone's kind of seen this before. Spearfishing, not something that a lot of people do themselves, but if you're standing in water, you can see that your feet are not where they are supposed to be. One of my favorites, the disembodied head. It's a nice little example of refraction of light. So yeah, so that's kind of the concept that herds light in the direction that you want on a microscope. So refraction itself is described by Snell's law, which when simplified is just N equals CV, which is index of refraction. which is a constant. So in air would be 1, and then water would be 1.33 or whatever that is. And then you have c being the speed of light and in the vacuum, and v being the speed of light in the particular medium. And this can be calculated based on this angle here, theta and sine theta, which is calculated from the normal, excuse me, the perpendicular to the medium, the entry into the medium. And so that's pretty basic. So how does this help us in terms of a microscope? Well, basically we use elements constructed, just making use of this refraction to again herd the light in a particular direction, and it's just a basic lens. When I say basic, there are of course very many different versions and different types of lenses, but in generally speaking, this is how we get light going from place to place. So this is an example of a thin lens, so-called perfect lens in the real world, where you have parallel rays hitting this lens, and then a refraction happens, and all lenses have a focal length, or at least an f, where all the rays should converge to the axis if the rays are parallel. So of course this all depends on the refractive index of the particular glass or whatever that material is, and of course the curvature of the lens. So this is as basic as a lens as you can get. So getting to a little bit more complex, an objective lens is just made up of many different lenses, and all crammed into a small metal body. And you can see the complexity in the interior diagram, which explains why they're so expensive and so heavy. So less concerned about what's inside at the moment and more about what's on the outside. So the objective lens is kind of something that people don't quite think about. Most people know about the magnification and just kind of follow that. And that's not necessarily wrong, but it's obviously ignoring a lot of things that could help you choose a better objective, or at least understand what you're doing. So we have the manufacturer, of course. This line we're going to get to a little bit later is all about the corrections to the different aberrations that could happen. Magnification, and this little number here, usually put next to the magnification, is the numerical aperture, is probably the most important thing on the lens, and we'll go into that a bit later. Whether or not this is what media it should be in, oil, air, etc. If it's any special features on it, the working distance and how close you can get to the sample before you're in focus, and 0.17 there would be probably the reference to the cover slip. So some lenses here have a color correction, and what's the color correction? It's to correct for various thicknesses of cover slips or cover glass that you put on your sample. And unfortunately, yeah, there's quite a few different cover slips, but we try and train people, at least to tell people to stick to the 1.5, because that's the most common. Not all lenses have this color correction, and they'll be stuck on a certain number, and most of them will be on 0.17, which has a general range between here. And you have to realize that especially for the higher numerical aperture lenses, changing up your cover slip in either direction will really mess up your imaging. So you have to keep an eye on that. I know a lot of you are in labs where you just have a junk drawer full of cover glass that you just kind of grab without thinking. So just make sure you just keep an eye on that before you end up mounting a bunch of samples and then regretting it. So talking about numerical aperture, a concept itself, we'll start off with resolution and what it is. So a rule of thumb for resolution can be explained by the Rayleigh criterion, which simply states that it's the resolution limit. The limit of the resolution is defined by the distance d, which two objects can be separated from each other in order to distinguish themselves, that there are two objects. So you can see here 1 and 2 objects. At this point, you cannot see that they're really 2 objects. Can be explained by this simplified equation. 0.61 is a constant, then you have lambda that represents the wavelength of light and the numerical aperture. So when we're talking about numerical aperture, it'll be easy to talk about the concept if you know what an airy disk is, or at least the concept of an airy disk, which is simply just, it describes the best focus spot of light you can make with a perfect lens. So you can't really get a perfect spot because of the diffraction of light and various things. You get a pattern like this called the airy disk pattern. And if you see it in a side view, you can see the most of the intensity happens in the what we call the zero order. That's about 84% of the intensity there. And some of you may be familiar with the word, with at least airy, in that airy unit, and the pinhole that you use in the confocal microscope. So when you see a pinhole setting at 1 airy unit, it basically talks about letting through this particular zero order here, letting through that for that particular wavelength. So that's kind of where the airy unit comes in. So numerical aperture can be explained in this equation, which is n being the refractive index of the medium, and sine theta, which is the maximum angle of acceptance. So you can see here the theta is just measured from the normal. That's the angle times the refractive index. And you can see here that as the theta increases, so does the numerical aperture. And the other thing that you notice that this cone of light gets kind of steeper and steeper, or at least gets smaller and smaller, and in that case, until it gets really, really close to the sample. So for those of you who've used air lenses and objective lenses, you can be quite familiar with this, where you're starting out pretty far away, then you end up being jammed 140 nanometers away, well, sorry, microns away from your sample. In terms of airy disk, as you increase numerical aperture, now your zero order or your entire airy disk is now shrunk down. So going back to the previous slide, if you can imagine if you had used a higher numerical aperture lens, you would be probably able to tell the difference between these two, at least separate them enough that you can resolve them. So the one kind of misconception, I guess, is that numerical aperture and magnification are one and the same. They are not. They are very much related, but they are a concept that it's kind of complicated nowadays because there's a lot of technological advances. But basically, if you're talking about an air lens, yes, there is a kind of a relationship in that when you increase your magnification, you do increase your numerical aperture. And of course, you see a lot more glass there. When you deal with different other lenses that require different immersion media, things get a little bit kind of not so simple. And nowadays, you have lenses that have low magnification and high numerical aperture, but those are kind of for multiphoton and tissue clearing. And they have put a lot of glass in there. They're very heavy, they're very big. And you usually need a very high refractive index media to get them to work. So, so this is just to show you the relationship between the two. So this is a quick little, I'm going to take off the laser pointer because it never works if I don't do it. Okay. Right, so this is just a quick little video to show you the relationship between refractive index and immersion media. So when you're starting off here with an air lens, because n is 1, so the refractive index is 1, and you can see that the cone of light here is pretty steep because it's got low numerical aperture. And if this is your slide and this is your cover slip and this is your sample, a lot of this, the signal ends up being refracted away by the glass and ending up even having a total internal reflection here and ending up kind of going anywhere else but within your microscope or into your microscope and detector. So I'm going to start the video now. And just keep an eye on the rays of light and of course the cone of acceptance there. you can also start to see that little edges here of what should be an immersion media. So around about back there, that would have been water at 1.33, and now it's probably oil of some description. And you see now the rays are not being refracted at all and making it into the objective. That's because now you have oil, which is a very similar refractive index than glass, so it really doesn't have anywhere to refract. So this is kind of how immersion media works. So we'll talk about some optical aberrations first, or next. Actually, I think this is probably a good time to stop to see if there's any questions. So I'll see whether or not any questions?
Please raise your hands if you have a question. It's good.
We're good.
5 seconds. 3, 2, 1. All right, move on.
Okay. Okay, let me try that again. Optical aberrations, where are you? Here we go. Nope, that didn't work. One more time. Okay. So there are two main types of optical aberrations, spherical and chromatic. So spherical aberration simply describes when the lens focuses the different parallel rays to a different location along the optical axis. So instead of a perfect F, you have kind of a mess or a jumble of rays that are not actually being focused into a focal plane here. So if you had a perfect lens, of course, like the diagram I showed you before, it would be perfect in a way that it will focus all of the different rays of light into a perfect focal point, an F. So of course, in the real world, there's no such thing as a perfect lens. So how do you correct for this? Well, you basically use a combination of different lenses before and after to kind of correct and help the all those rays come to a more perfect location, or not perfect, but a better F location. And that's kind of how you deal with spherical aberration. The different type, the other type would be chromatic, and in the same kind of way that there's no perfect focal point, but now we're dealing with the different colors of light or different wavelengths of light. And this is going to happen when, if you use a broadband light source that has a lot of different wavelength content to it, or if you're using monochromatic lasers and you're firing in different lasers all at the same time, and they don't quite all focus at the same point. And this is going to be a problem if you're trying to do something like co-localization, or you're trying to find out if two things are in effect on top of one another or next to each other. So how do you correct for something like that? The same way you did for the other type of aberration, you throw more lenses at it. And basically, the different lenses that you can put in combination have different qualities or refractive indices or coatings that kind of help all those colors land in the same place and get collected from the same place. So you can see the kind of different naming systems you have. So the fluorite, aprochromat stands for the type of color correction that you have. And then the plan indicates that it's been corrected for spherical aberration and flatness of field. And of course, you see that the best here is plan apochromats. And in the facility, we try and buy as much as we can, even though, of course, they're the most expensive, fit out the microscopes with plan apochromats where it makes sense. But just for you to remember when you're looking at using different microscopes and different objective lenses, you check whether or not, if you're going to be doing a lot of multicolor stuff or you need a lot of flatness of field, exactly what lens you'll be using. So with saying all of that, you can imagine there is a ton of lenses out there. it could get a bit confusing. So which objective do you end up using? So there is general rules, but of course you really have to sit down and figure out what you want. So you want to use high NA lenses simply if you need better resolution. Better resolution and better sensitivity in terms of being able to collect more light. And usually the high NA lenses are the ones with immersion media. The downside is, as I mentioned, that the higher numerical aperture, generally speaking, the smaller the working distance. So you want to make sure you don't end up, you don't try and image a thick sample through a chamber or a cover slip, because you're going to end up running into the sample as you're trying to get closer and closer. Of course, you can use, if you're doing thicker samples, there are high, you can take a little bit of a hit in NA, but still have a high numerical aperture. Now, if you need a large field of view, a long working distance, or a large depth of field, you use a low NA lens. So the depth of field is another thing. If you have a high numerical aperture, things fall in and out of focus very, very quickly, whereas a lower NA, you have a larger depth of field and things stay in focus a lot more. Now, the argument that you need a large field of view for numerical, for low NA lens is not quite true anymore, because, well, especially in most modern microscopes, they come with tiling and mosaic or stitching software or features that allow you to use a high NA lens and stitch a bunch of them together pretty quickly to give you a large field of view and a very good, very high resolution. So just think about what you need. If you don't need intracellular resolution and tiny resolution, and you just want to see where the cells are, then, well, just use a low NA lens. No point going crazy, right? Resolution and Nyquist sampling. This is something that we, again, try and tell people to do or think about. Basically, make your first attempt your best attempt. We don't want you to be sitting on a microscope and trying to get through the imaging and just doing low-res imaging, only to regret it later. So we, to talk about resolution and sampling, we go back to the Rayleigh criterion. Let's talk about just the wavelength part of the Rayleigh criterion. So in this example, this is tubulin, and it's stained with two different antibodies, or two different, secondaries. One is with Lexafor 488, and one is with 647. Everything else remains the same. And you'll see that, well, obviously, this is a lot better of an image, a lot more resolution. That's, well, basically because it's a shorter wavelength, and you can resolve a lot more, because of this relationship, you can resolve a lot more features with a lower or shorter wavelength. Now, there are pros and cons, obviously. Cons being that the shorter wavelengths have a higher energy, and higher energy means that you have more chance of photo bleaching. And of course, with a lower or shorter wavelength, you decrease your depth penetration. So this is just something for you to think about if you have, if you have only a single stain, you want to use something a little bit lower if you can. I keep saying lower, I mean shorter wavelength. And if you have multi-labeled samples, then perhaps label the feature or your target that you're most interested in with a lower wavelength. I said it again, I mean shorter wavelength. So the Nyquist-Shannon sampling theorem is a concept that is difficult to, well, it is simple in theory, difficult to get across, and difficult for people to kind of to care about, really. But it is a theorem that persists throughout a lot of different fields. But if we want to go through this quickly, the Nyquist criterion basically requires you to sample at an interval twice the highest specimen spatial frequency, all so that you can preserve the spatial resolution of the digital image. Shannon sampling theorem is related to that. Basically, you need to have a digitizing device, and I'll talk about digitizing devices a bit later, that utilize a sampling interval that is no greater than 1/2 of the smallest resolvable feature. Simply put, you just want to, if you want to make sure to capture the smallest detail or in your specimen, you want to make sure that you sample at least 2 samples per specimen size, just to make sure that you have enough light and dark portions to your sampling that you can tell that is a feature that you have. So, I mean, if you have a 200 nanometer object, you wouldn't put down a 200 nanometer pixel, because then you just get a big pixel. What you would do in this case is to put down 200 nanometer pixels. This is oversimplified, but you put 200 nanometer pixels on your 200 nanometer object, and then you would say that you are at least sampling it correctly. So so that's kind of what I was saying. In optical microscopy, the limit of resolution, according to Abe, is around about 220 nanometers. So you want to make sure that you put down enough pixels, in this case 110 or less, to be able to capture all those low and high intensities and the special frequencies that surround that. So there is a point of diminishing returns, or you can oversample. Basically, you can put down a ton of pixels when you don't need to. However, these extra pixels, while they don't contribute to the spatial resolution per se, they will help you improve the accuracy of feature measurements at a later stage. As such, even though before the simplest Nyquist Shannon sampling asks you to do it 2 times, it's to be on the safe side, you want to do at least 2.5 to 3 times of the smallest resolvable feature. So, so again, if you have a 200 nanometer thing or object, you would put down like an 80 nanometer pixel across it to be able to really sample properly. So a lot of software now have these buttons that just, you don't even have to think about it. You can just kind of click on it, and it will, given your particular circumstances and your lenses that are involved and filters and wavelengths, you just click this button and it will fix everything for you to make sure that you're sampling properly. So you don't really have to think about it in a lot of cases, but you need to understand why it's doing that. So I'm not going to talk about deconvolution now because we'll be talking about it in a subsequent seminar. But it basically it's a concept that restores your images by reverse engineering all the optical aberrations in your system to be able to give you something that can be pretty much defined as super resolution, basically. So, but for deconvolution to happen, you really need to oversample to make sure that you have enough information, per pixel information, to give you that nice image. So how do you increase spatial resolution? If you are assuming you have the same optic, you don't change your objectives and your filters and whatnot, well, you can just increase your pixels. So this is, again, another exaggeration. This is I found out that this is a baby starfish. If you put down 11 by 11 pixels, you obviously cannot see what's happening there. Double the amount of pixels, 22 by 22, and so on and so forth, you are now able to see exactly what you're looking at. Upside, it preserves the field of view by putting down more pixels in denser pixels. Con, you really decrease your scan speed. Now, instead of going across 11 and 11, you really have to put down, and this is in terms of, well, more to do with laser scanning, which I'll get into a little bit later. So you do lose your scan speed. With field zoom, that's another way of increasing a spatial resolution. Well, now you are, instead of, say, 512 by 512 pixels, if you put down those same 512 by 512 in a smaller space, you are now reducing the size of the pixels and sampling a lot denser, and your resolution will increase. Pro, your scan speed increases. Obviously, now you're putting down the same number of pixels in a much smaller area. The disadvantage is, obviously, your field of view decreases. So let's not forget about axial or Z resolution, and this is especially pertinent for people who use confocal microscopy and use the confocality of a laser confocal microscope. So when you take a 3D volume, a Z stack, you take your images at different planes, and you can kind of collapse them together to give you your so-called Z stack. This is the same in terms of Nyquist sampling. If you undersample and don't take enough slices to constitute your volume, you end up undersampling it, and you're not really showing what your true kind of Z direction resolution is. So you want to do the same thing. You put down a lot more slices and correctly or oversample it to represent what you're trying to see. Now, again, there's a limit to this, and there is also diminishing returns. Microscope software also help you with this, but if you care about your Z direction, you need to be able to sample properly. Simple as that. So, digital sampling and dynamic range. Again, another concept that people really don't understand too well and don't really think about when they sit on the microscope, and which is a shame, because it really hampers you if you don't do this properly or don't think about this when you go off and doing really high level data and image analysis. Because everything is there for you on the microscope, and it's just there for you to know what to do. So I'll talk about different types of detectors and the digital sampling, and then I'll talk about the dynamic range and bit depth. But before I talk about that, I think this is a good time to stop again if there's any questions. Guys?
Raise your hand again if you need clarifications on some topics.
Obviously, if you don't want to speak up now or write anything, we are available. Just email us, and you can talk about this later. And just to mention, we are recording this, and if all goes according to plan, we'll upload it to YouTube somewhere in a private link, and we'll make the slides available to everybody.
So yeah, everybody knows how to pick a good objective in terms of numerical aperture or field of view, which cover slip to use, how the objectives are corrected for color, for planarity, their working distance, how does the wavelength affects the resolution, what is Nyquist. You guys all good?
I guess so.
All right.
Right. Okay. Okay. So this is we'll start off with digital sampling. So this is the concept of how you get an image, simply put, on a microscope. That where a microscope, at least, where you don't use your eyes. If you're on a microscope that has a detector of some sort that isn't your eyes, then this is what happens. You have your analog image, and you go through two processes to get to the point where the system understands what it's seeing. So first you have digital sampling. So it puts down pixels in what you call a Cartesian coordinate. And then you have, this is the analog to digital part of the conversion. And then the subsequent step here is what they call pixel quantization, where it assigns an integer in terms of the intensity of that pixel. So here you see that the lighter parts or the background has a higher value, and the darker parts have a lower value. So that's simply how you get from an analog image to pixels and kind of integers and intensities and numbers. So this always has to happen when you have a detector that other than your eye. So let's talk about the first type of detector, point detectors. So point detectors are most prevalent on confocal microscopes, laser confocal microscopes, and they are photomultiplier tubes and photodiodes, and they lack spatial discrimination. So what this means is they're just simply light detectors. They don't know where that photon came from. They don't care. All they do is they grab that photon and they kind of amplify it. They amplify that signal. So how does this help us find out where things are? So we deflect that beam. So when we have that laser spot here, we use something called raster scanning, and we scan that beam from left to right, and then we swing back, so the horizontal retrace to the next line below, so on, so forth, until you get to the bottom. Then you swing all the way back up to the top left again, and repeat. So you can imagine at each point, the digitizer has to, and the clocks that are involved, the analog to digital and the timing clocks have to make sure that they know the coordinates of where that pixel is. So at this pixel, it'll be at a particular intensity. In this pixel, so we bring this up again. So imagine this swinging through, and then at each point, each pixel, it needs to tell the computer an integer value of that intensity. So obviously the timing clocks have to be absolutely on point here. Area detectors, on the other hand, which most people are familiar with in terms of cameras, they consist of a dense matrix of photodiodes in an array pattern, which incorporates various charge storage regions. So this is an exploded diagram of the two kind of sensors, monochrome and color. And basically, as I mentioned, there's an array of photodiodes, some lenses. For the color sensor, you have a color filter, an array of color filters over each pixel array, or each pixel. And the two different types of image sensors, generally speaking, are the CCD and CMOS. Won't go into the differences now, but it's just a different way in which they get a photon, or once it accepts a photon or detects a photon, how it converts that to a charge and subsequent voltage, and then digitizes, et cetera, et cetera. So area detectors do have spatial awareness in that your image is kind of projected over the top of this array. So dynamic range is everywhere. A lot of different fields use it, sound, light, and there were a lot of definitions of what dynamic range was, but the simplest one that I could find was that a dynamic range of a system provides information on the lowest and highest intensity signals that detector or sensor can record simultaneously. So it's just a range of the lowest and highest and everything in between. So when we're talking about digital sampling, we have our favorite image here again. As some of you may have noticed that the numbers don't get any higher than, say, 255, and that actually talks about bit depth. So when you talk about bit depth, it relates to grayscale levels, and you get your grayscale levels by going 2 to the power of the bit depth. So in this case, it was an 8-bit image because the values headed up to 256. And you can see the difference of gray levels when you go up in bit depth. If you have a 2-bit image, you have only 4 gray levels to work with. And if you imagine if you only had 4 levels to work with, that image would not be very, very good. And of course, subsequently, if you increase your bit depth now, say for an 8-bit image, you now have 256 gray levels in which to have a distribution of intensities to have a much nicer image. So I've highlighted these in yellow because they're the most common, at least in terms of the digitizers or the cameras and the detectors that we have, at least in our lab. And we have everything from 8 all the way up to 16. So you can see the differences there. So if you want to put this graphically, you can see, say we have an analog signal here. And so how would we digitize that to represent that analog signal? So if you put down enough samples digitally, you can at least get a good representation of what the original analog image is, or analog signal. If you undersample, or you don't have enough of a bit depth, then obviously this does not represent what your original signal was. So put in kind of real world examples. Here you have a 1-bit image, so that's 2 to the power of 1 gray levels. You have black and you have white, so not very good. You start to increase your bit depth, and now you can see that the background starts to become background, and you start to have various features pop out of the image. So bit depth is important. Bit depth is hard-coded into the digitizer or the hardware. And bit depth is completely useless if you don't use it to the full potential, or that dynamic range that digitizer gives you. So when we train people up, we always make sure to hop on bringing up the histogram. And why is that? Is because it's a very quick visual representation of the distribution of intensities in your image. Now, a lot of microscopes nowadays, at least the software, like to play different tricks, do different things to make sure that your image looks really nice on screen. Now, of course, things can make anything can be made to look good, but the histogram will never lie. So here, the image looks pretty good and it's got good contrast because there's a nice kind of even distribution of the higher and lower and mid intensity levels of all the pixels in the image. Now, if you have a low contrast image, it means that you don't have much of a distribution. You've kind of just crammed everything into a one spot there. A lot of people will not fill up the dynamic range by not, say, using enough laser power or gain or detector gain or exposure, and end up with a lot of stuff here. And what that means is that you're just underutilizing the range that's given to you. And you end up with something like this, especially when you play with image analysis and you try and play with a threshold. All of a sudden, your background is pretty much the same as your feature or your target, and then you're in trouble. And of course, you have high contrast, where basically you have too many pixels in the low and high. What I want to point out, there's also saturation in these cases. And saturation just means that you've saturated detector. You've gotten past the bit depth or the dynamic range that you have. And what this means is you've compromised your data. You've no longer are within the working range of that detector. So that's the one thing you have to think about every time you sit down on a microscope. Make sure you use the dynamic ranges given to you. Don't saturate. So that's kind of the tip that we want to give you. Very quickly, for those of you who are using color cameras, as I mentioned, it's just a monochrome pixel array with color filters over the top of it called a Bayer filter in most cases. And if you looked at the histogram, you'll actually see that it's a combination of the three colors according to the filter, Bayer filter. And you still, even for bright field images, you want to make sure that you fill that histogram because it's still a sensor and it still has a bit depth and it still has a range. So an analogy I decided to use for basically for dynamic range and for the resolution is one attempt Lego. So imagine if you're given the task of building a giraffe out of Lego, and you had one go at it, and we're giving you a bucket and a pile of Lego, and we asked you to go away into another room and build it. If you're in a rush, you just grab a handful, throw it into the bucket, and move on. And what you end up with is a pathetic thing like that. So it is a giraffe in all manner of speaking, but you obviously could have done a little bit better. If you took the time to fill that bucket, then you have a much nicer giraffe. Now, I don't know if that analogy works for everybody, but to me, it just means that just spend a little bit more time on the scope, get the best resolution you can, and you won't regret it. And basically, the image analysis won't look like garbage, or you'll get something that's actually useful instead of having to go back and re-image your samples. Okay, so stop for questions again. If there's anything, those concepts are a little bit more difficult, but yeah, anybody have any questions up there? This is the last section.
I have one question. I wanted to understand the relation between bit depth and resolution. And so, just for practical considerations, that if I want to image faster and have a smaller file size, would increasing bit depth and slightly reducing the resolution help me? And at the same time, when I can also capture all the relevant data?
Well, if you're going to go fast, well, if you care about file size, then increasing bit depth. If you're on a microscope that can actually have different bit depths, then the higher the bit depth, obviously there's more digital information, so your file size will increase quite a bit. That being said, you won't see any decrease in or increase in speed or decrease in speed. You have no speed changes because it's just digitizing the data. Sorry, repeat the question again. You want to be quicker, and have less file size?
Yeah.
Okay. Well, that doesn't really work.
Yeah, but I know that, just trying to understand that, if I increase the bit depth and reduce the resolution,
well, you can increase your resolution by everything that I just mentioned. You can reduce the scan speed by having a smaller field of view if you can afford that. You can increase your resolution, especially like putting down more pixels, but that actually will decrease your scan speed. I assume you're talking about confocal scanning here. Yeah. So there's a lot of different things you have to play with. It's all a compromise, unfortunately, but file size shouldn't really be an issue. I mean, is it an issue for you?
Not really. I mean, yes and no. So if I have to like process my files on my personal computer, which is not as fancy as our imaging or image processing computers, then, if I'm opening my confocal scan in my Zen program, then it takes a while,
That's completely understandable. We've all been in that situation. That being said, it's always good to take a higher a high bit depth image or use that full dynamic range, because at any point afterwards, you can downsample. I mean, that's not the best thing to do, but you can downsample the image from a 16-bit to an 8-bit image, and you lose you lose some stuff in there. I mean, there are ways around it. You can do what I just said, or you can, we're going to make it so that you can remote into a better computer.
So let me give a few more points here. So if you're talking about spatial resolution, if you want to image faster, then basically you need to figure out what resolution you want. All right, so if all your objects are 5 microns, then your pixels need to be about 2 to 2.5 microns. And so this is fairly low NA objective. And this low NA objective is going to image a large field of view, so you'll be able to image pretty fast and so on and so forth. Now, if you need the maximum resolution you can get, then you can't do nothing. You have to go to Nyquist. Okay, so that's for spatial resolution. Now, when you're talking about bit depth, whether if you want to reduce your image size, and your microscope allows, or your detector allows, like anything from 8, 12, or 16, you can pick the 8-bit dynamic range, or the 8-bit depth. Now, what's going to happen here is, what you want is make your dynamic range of your image very wide. And the reason is you want to discriminate your background in your image, so what you're not interested in, versus your foreground, so all your objects. Now, if you have a very restricted dynamic range in your image, you will not be able to discriminate the two, right? So in that case, let's say you have 40 counts on your normal image, okay, at 8-bit, out of 255 counts that it can have. Now, you're going to slow down your speed by, say, increasing your pixel dwell so that you get more counts for each pixel, raising it to, let's say, 200 counts per pixel of interest, right? Now, it's going to slow down everything, but now your dynamic range is going to be improved, staying at 8-bit still, and so you're going to be able to discriminate your objects and your background. If you really want to not compromise on speed, in that case, what you could do is crank up either your laser power or crank up your detector amplification. But then you might, in terms of amplification, you might generate some noise. In terms of laser power, you might bleach. So it's all a compromise at the end of the day.
Yeah, I would, I kind of, like, I knew all this, but in the sense that, just trying to understand what is the best combination possible if there is any. So yeah. But yeah, thanks. That was a good explanation. Thank you.
Yeah, good question. Short answer is no. There is no perfect combination. Really depends on what you have. We can push you in the right direction at the very least. But anyway, this is let's just keep going. This is the last section here. We'll get through this pretty quickly. But so system alignment and experimental repeatability. So when we talk about this, when you make your samples up in your lab, when you're preparing your samples, if you make it a point to use the same dilution of antibodies, primary, you want to make sure that you think about repeatability on the microscope as well. So as I mentioned, it really matters about your cover slips and your mounting media, because this can all mess things up. So you have to be consistent when you do that. On the microscope, especially the modern ones, you almost don't have to think about it, because you can save all your parameters, laser power, gain, filter sets, combinations, and you just bring them up. Now, that's fine and good, but there's no guarantee that everything is still the same, and I'll explain why. So let's talk about it in terms of laser confocal microscopy and the things that can go wrong. So this is the laser launch. Every confocal microscope will have some box that has all the lasers in it. And it deals with everything in terms of choosing which wavelength and how it attenuates or how it plays with the power. So you have a bunch of lasers, bunch of mirrors and lenses, filters. It all goes into a box, usually called an acousto-optic tunable filter. And all that does is it helps you choose wavelengths and helps you play with power. Now, when it comes out of that, usually it will be coupled into a fiber, a single mode fiber. A single mode fiber with a core diameter of less than 10 microns. So you can imagine that the alignment of everything is absolutely needs to be on point. And usually these lasers at its source, they are rated between 10, 100, maybe some even 200, depending on the wavelength that you need. So after that, if it makes it out of the single mode fiber, it has to go into the scan head. And once it goes into the scan head, it goes through extra filters, extra glass, extra optics, before eventually getting to your actual sample. And right at the beginning, that single core, that fiber will absorb around about 50% of that laser power. And then every piece of glass that it goes through and filter, it absorbs some more. So what you end up with is no more than about 3 milliwatts at your sample. Now, what I'm trying to demonstrate is alignment is very crucial, especially when it couples into that single core fiber. Now, if you want to make sure that everything is repeatable, yeah, you can bring up all your parameters again, but can you ask yourself, is a 5% laser still 5%? And you'll never know that if you don't know what actually comes out of that objective. So what we try and do is to make sure that we always measure the power that comes out of that objective, because that's what matters. So we use power meters like this, which are shaped like slides, and then we put them directly under the microscope objective, and we basically measure the power there. Now in the facility, we do this as frequently as we can. Of course, some of the busier instruments, we can't get onto that often. But if you're concerned, we can teach you how to do this yourself. This one's more useful for visible wavelengths, and this is more for multi-photon and high-powered lasers. But just wanted to get across the idea that nothing is as stable as you think. We make sure that we have system engineers come in and align everything as best we can. But if your experiment is very crucial in terms of the power that you put down, then you want to make sure that at the very least that the laser power you're getting at the sample is exactly what you have from the beginning and end of your experiment, especially if you come in over several months. The last thing I want to talk about is just a comparison of wide field. So I talked a lot about confocal laser microscopy. Now, in confocal or laser confocal, there are a lot of parameters that you can play with, from the laser power, of course, the filter sets. You can play with the pinhole, you can play with the PMT or the detector gain. In wide field, a lot of our systems are pretty limited in what you can play with. Of course, you can choose your objective lens and stick with that. But the only other thing on most cases is you can play with the exposure of your camera. There are other things you can play with, gain, pixel binning, lamp excitation, neutral density filters, but they are usually not available for good reason, because it kind of muddles up the parameter space. While wide field alignment is a little bit more forgiving, because instead of single core fibers, it's a little bit more easier to get the light through and back again. You have a lot less to control. So if you're using wide fields, so like the slide scanner and stuff like that, you want to make sure that you have all your parameters the same the whole time, especially your camera exposure. So in summary, again, not exhaustive, but if you're getting onto a microscope, what we wanted to do was just to give you an idea of all the different things you get into your head before you start the experiment. And if you get into a habit of this, then you don't have to think about this every time, obviously. But we want you to get the most out of the microscope so that when you get off that microscope and end up trying to analyze data for 3 months, that you actually have useful data, or data that you don't have to go back and re-image. So when you get onto the microscope, you want to at least wait a little bit before you get on and actually start using. Lamps, it makes sense. Lamps need to warm up. Lasers as well, you don't realize that they're not super stable when you turn them on completely like cold, because there are current fluctuations. So they're pretty good nowadays, but there's no harm in waiting a bit. Objectives. We want to make sure that you know what objectives you're using and why you're using that objective. So consider everything: numerical aperture, magnification, field of view, working distance, immersion media. Once you figure that out and you know what you're doing, then you really don't have to think about that. For detectors, and we're talking about dynamic range here, for confocal detectors like PMTs, we want to aim for between 60 to 75% of your available range, whatever that bit depth is. This is not a hard and fast rule, but we just want to make sure we give you a good kind of ballpark figure to not saturate your image, but at least to try and use as much of that dynamic range as possible. For wide field cameras, we found no matter what the bit depth, try and aim for at least 3,000 counts. Now, this is not always possible because now you're dealing with exposure, and more exposure means more bleaching. But you want to make sure that you try and get as many counts as possible to get a good signal to noise ratio. And always check the histograms. The histograms will give you a quick idea instead of numbers, and especially not images will give you that right kind of idea of what your intensity distribution is. Nyquist sampling, as we tried to get across, you want to make sure you put down enough pixels to represent your image. Put down enough pixel density in whichever way you choose, in X, Y, or Z. And you can choose doing that through, as I mentioned, either through field zoom or pixel density. You can calculate it manually or use whatever software gives you. So you really don't have to think about it here. And I've put the arrow here because it's a bit of a feedback loop. If you end up playing with pixel resolution and field zoom and confocal, you're going to end up having a different dwell times and scan speeds. So your range is going to change. So you're going to have to keep checking that if you play with it. Lastly, with repeatability, you want to maintain consistent sample prep. So you want to make sure, obviously, to use the same mounting media and the same thickness of cover slip every time if you're going to be using the same experiment. Because if you start to mix and match, you're going to get very bad results. Keep all parameters the same. That goes without saying. And that laser power may not be the same month to month if something bad goes wrong. Of course, we make sure that it is the same month to month. But things like environmental factors, going from winter to summer, imaging in the morning instead of the evening, imaging alone versus a full lab, this matters as well because the heat load is different. So there's a lot of things that can affect the system. We're not telling you to be paranoid, just to be aware. I've put down here to write your parameters down and don't rely on embedded data. We've had some issues where, if you export your image as a TIFF or a JPEG, then that metadata is no longer embedded. So better safe than sorry. Write that stuff down and you won't regret it. Finally, make your first attempt your best attempt, and you don't have to be going back all the time to redo your imaging. So that is it. Gone a little bit over time, but it's not too bad. So all the information that we have, just visit our website because we try and update that regularly. All of the, well, most of the images and the examples I used can be found in all the major manufacturer websites, educational resources, which we have listed in this link here. Any questions, again, you can email us and we'll get back to you. These are the subsequent seminars that are happening. The next one, again, the dates are tentative, but probably will stay the same. Next one will be digital imaging and how to segment and automate and batch process everything. And that's it. So let's if anyone has any questions before we end this.
There's a few questions, Kevin. Number one, what may lead to a high contrast histogram?
What may lead to that? You know, that's a good question. When I saw that example, I don't think I've ever seen that before. Have you seen that before?
You mean me?
Yeah.
Yeah, it's well, yeah, I'm not sure the example was the best one out there. If you want, basically, the more contrast you have between your structure and your background will depend initially on your sample prep, right? If your signal is very bright versus whatever else, say your tissue autofluorescence or whatever media your cells are in, then this gonna likely lead to a higher contrast in your image. That being said, if you have, I mean, black and white, like a 1-bit image, it's either black or white, is the highest contrast you can have. So if you shrink your histogram, usually it leads to higher contrast. Yeah. But if you want to differentiate different structures that have different light intensities, then you need a few more counts, or to spread out that histogram.
I can see the next question. Is this the cover slip question?
Yes.
So not that I'm aware of. Cover slips are made of glass, and I am not aware of any glass that has a refractive index of less than 1.5 or less. I assume that maybe you want to do some live imaging, or I'm not sure what your sample is, but if in the case where if you need it to, if the cover slip is getting in the way, get rid of the cover slip. Of course, if your sample is fixed and mounted correctly, a lot of people actually image without the cover slip, and you get some nice images that way. Now that is if your sample can survive that, because if you cover slip, what goes along with that is mounting media, and a lot of mounting media have kind of bleaching protection, kind of oxygen scrubbers and reactive oxygen scrubbers to make sure that your dye or your antibody, or sorry, your secondary at least, will survive the beating that it gets from the excitation source. So you do kind of miss out on that. So yeah, that's my answer to that. Is that I hope that's good enough.
Yeah, I mean, if you're imaging in a well plate with a plastic bottom, for example, some plastics do have a refractive index that go a little bit lower than 1.5, more towards the 1.4, 1.3, or it can be as high as 1.7. But yeah, plastic bottom plates could better match the water.
I think that looks like that's it, right?
Yeah, so anything more in terms of questions, guys? All right, so next week, like Kelvin said, we're aiming for June 10th, and this webinar will be, we'll try to walk you through a few examples with ImageJ or Fiji. So if you do have if you do want to walk with us, make sure you have Fiji installed. We can help you with this. And then a follow-up is going to be with Immersion, which is going to be a demo. So it's hopefully from that point on, it's going to be much more applied type of webinar. That's what we're going to try, even though we're doing this remotely. So it's a little bit harder that way. It should be fun though.
I'm not sure if my chat worked, but the question is, how do we sign up for the next one? We'll put out a new Google Forms link for that, and then again, we'll put out the Zoom link a day before. So that's how you're going to sign up. Okay.
Awesome.
Okay, so we're going to stop the recording now, and thanks for coming, everybody. Stay safe, and we'll see you in a week or so.